This podcast is brought to you by LMU Munich.
Well, it's a pleasure to be here and to tell you about some results that have been obtained with Pavel Noselski and with our postdoc Hao Liu in Copenhagen. I should also say it's a particular pleasure, or was a particular pleasure for me to discover that this is a named colloquium, because I have a kind of personal connection with Arnold Sommerfeld, in that when I began graduate studies so many years ago, I was presented with all of the volumes of his course in theoretical physics, which intimidated me completely, because I didn't think it reasonable that one person could understand as much physics as Sommerfeld obviously did. And this image that's taken from the book was a photograph made instead of a lens with a circular sheet of metal. And I really understood the significance of this only later, when Hans Bethe, who of course was one of Sommerfeld's students, explained to me that Sommerfeld loved all physics, but particularly when it included Bessel functions. And to understand this problem, you really have to understand Bessel functions. But that has nothing to do with what I'm going to talk about today. What I'm going to talk about today could sound like something which is really more for a seminar than a colloquium, but I hope there are a few things I can tell you that may be of more general interest. I see students, as usual, have undergone a phase transition in the back. I tried not to put you to sleep, okay? Everybody knows that Einstein first came up with the idea of gravitational waves, which is not correct. Surprisingly enough, the very first person to come up with the idea of gravitational waves was a very strange character named Oliver Heaviside. You may have heard of him. He's the first guy to invent the step function and to use it. He was also the first person to really introduce the utility of complex analysis in dealing with electromagnetic problems. And in 1893, he wrote a textbook entitled Electromagnetic Theory, which was intended for electrical engineers, which was what he was. And in it, at the very end, he has an appendix on a gravitational and electromagnetic analogy. The idea was that on the basis of something as simple as the equivalent forms of Coulomb and gravitational interactions, that he asserted that there should be a complete analogy between gravity and electromagnetic theory, and that included the possibility of gravitational radiation. The idea, surprisingly, was picked up some years later by Poincaré, who we perhaps know more from complex systems than anything else. And very soon after the publication of special relativity, Poincaré came up with an argument that suggested the necessity of gravitational waves based on arguments from special relativity, which I think were spurious, but nonetheless he was convinced early on that there should be gravitational waves. And then, of course, in 1916 and 1918, Einstein really did the business. For those of you who don't know about gravitational waves, they're essentially quadrupole in nature, and what one expects is that we're going to have changes in the geometry. This is Einstein undergoing a gravitational wave, where you can see he's first stretched and compressed in one direction and then stretched and compressed in the orthogonal direction here. And that's what people would like to measure. Now, when I started in Princeton in September of 1959, there was another guest in Princeton who came to work with and talk with my first physics teacher, who was John Wheeler. And that fellow was a guy by the name of Joe Weber, who I suppose not so many of you have heard about. But Joe Weber built what he called Weber bars. Now that sounds like a candy of some kind, but it wasn't. It was an aluminum cylinder of size roughly 2 meters. And Joe Weber claimed that with 2 of these cylinders, he could measure relative shifts in the sizes at the level of a part in 10 to the 16th, which is really pretty impressive, given that LIGO these days claims to measure things down to 10 to the minus 18 meters. They're 2 orders of magnitude better. I'm not sure he was ever correct about this. Well, Weber came and he was excited by the ideas of black holes. He met a friend who was a friend for the rest of his life, Kip Thorne, who I think you know is very much involved in the LIGO experiments. And he became so convinced in this that he built his Weber bars and set about making measurements, potential measurements of gravitational waves. The first time I heard Weber talk about this was sometime in the mid-60s when he was beginning to get underway. He had two of these bars set up on the eastern shore of Maryland, which is a very desolate area. And the first excitement and the first discovery of gravitational waves turned out to be a young undergraduate and his date who had discovered their laboratory hidden in the woods on weekends. And that wasn't actually a discovery of gravitational waves. But nonetheless, a little bit later, in 1968, Weber came with the first Physical Review article in which he claimed to see gravitational waves, and followed it up here roughly 2 years later with another Physical Review letters. At this point, he was associated with the Institute for Advanced Study, where he claimed to find no less than 311 gravitational wave results. This was, of course, extremely exciting, and everybody began to produce their Weber bars and make measurements. And very shortly thereafter, the conviction grew that what he had seen was not correctly interpreted, that his statistical analysis was wrong, that there was no evidence whatsoever. So the data could not be reproduced. No such discovery could be claimed. It was a long wait until not so long ago, BICEP 2, sitting down in the South Pole, once again discovered gravitational waves. They did so by measuring polarization in the CMB data, and were very, very excited. As usual with such a discovery, a major press conference was held, but unfortunately, within just a couple of months, people from the Planck team studying the cosmic microwave background made a very compelling case that what had actually been seen was the polarized thermal emission from galactic dust. It was a foreground effect. It wasn't the genuine effect of gravitational waves. So two discoveries, not. And so the question is, what should we make of it when we come to the latest one with LIGO, who published this at the same day that they held their press conference, claiming not only the discovery of gravitational waves, but also the clear indication that what was seen had been due to the merger of two black holes of mass 29 and 36 solar masses, with the impressive amount of gravitational wave radiation corresponding to 3 solar masses, which is really quite impressive. The power output at that point was really impressive. Okay. The question, though, after 2 of these discoveries that it didn't work, should we believe it? And that's what I would like to address today, this question. Now, since the publication and announcement of this discovery of gravitational waves, several things have happened. One is that somewhat later there was a discovery of a second event on the day after Christmas in 2014. And there have been something on the order of 1,200 citations for this initial paper, which is very impressive. And one of the questions that I found interesting was how many people have actually bothered to take a look at the data on which the conclusions were drawn out of these 1,200 papers. And as far as I could tell, there were 2, and we were involved in writing them both. Now, everybody knows these days that when you have major experiments with major expenses, and by the way, the cost of LIGO is approximately $1 billion US. It's not trivial. That the National Science Foundation puts certain requirements on making data public, and as I'll show you in the course of this hour, the data here is extremely simple. It's a one-dimensional time record, and so anybody can pull it down. It's on the net. You can easily have it on your laptop, and all of the analysis that you might wish to do with this, you can do on any laptop going. So the question is, Why haven't people looked? And when you do look, should we actually believe now, for the third time, that gravitational waves have been discovered? It kind of brings to mind the old quote from Mark Twain, to the effect that it's easy to stop smoking. I've done it hundreds of times myself. And you could say the same thing about gravitational waves. It's easy to do. Lots of people have done it. They've done it once again. So let's just take a look and see what we can see. We have these laser interferometer gravitational wave observatories, LIGO, which are located in Hanford, Washington, and in Livingston, Louisiana. I think was not a design parameter, but it's extremely convenient that they're 3,002 kilometers apart, so that the time it would take for a signal propagating at the velocity of light to get from one to the other is 10 milliseconds. As close as doesn't make any difference. Each one of these is made, as you can see, with two different arms, which should measure through an interference effect length changes, which are claimed to be 10 to the minus 18 meters. It's a little hard for me to understand exactly what 10 to the minus 18 meters means in this context, since that's 1,000th the diameter of a proton. But okay, that's what the claim is. And again, since these signals are expected to be very weak, and we'll see soon just how weak they are, the idea with the two is, in fact, to make use of the power of redundancy. In this case, depending on the angular orientation of a gravitational wave, if the detectors lie on this plane, we could come in perpendicular to that plane, in which case there would be no time delay between the signals. The worst case would be if it came in the plane, passing through one, then it could take as long as 10 milliseconds to get from one detector from the other. So the idea is to look for two identical signals that are separated by something less than 10 milliseconds. And this can indicate, to say, that something has happened, which was not just an accidental event. But what it can't tell us, I would emphasize, is just what it is that has happened. And this has to do with some of the criticisms I want to make about the way in which the data has been analyzed. Of course, the idea we're going to define everything and measure everything in terms of the strain, which is to say change of length, relative change of length divided by length. These are 4 kilometers long here at each of these arms. And what we expect to see here are signals which are going to be the order of a change in length of one part in 10 to the 22nd. So they're not very big changes in length. And that will, if we see the same kind of signal in the two cases, this is to indicate for us that things are really there. There really is an event. Now I'm going to tell you a little bit about this in a moment. They claimed to find an event. Let's see, I don't want to go. Here we are. All right. They claim to find an event here. As I say, this is the data from Hanford, which is by far the better of these two detectors. They're not equivalent detectors, and we'll see how different they are in just a moment. And this is the signature here that they're looking for. In a sense, you see perhaps an increase in the frequency. The peaks get closer together. An increase in the amplitude, and then something that you could convince yourself was a ring down effect. It's clearer here, and something like this is the template that has come. It's their data. They say numerical relativity. Most of it is a classical calculation, as we'll see in a moment. And again, an increase in frequency, an increase in amplitude, followed by a ring down. Now, if there's any kind of a catastrophic event, this is an absolutely generic signature. Things will happen more quickly. They'll happen with an increase in amplitude, and then you'll come to some new phase, which is a ring down. So this is the kind of thing you would expect to see from any, let's call it, catastrophic event. Okay. And this is a cleaner picture of what the signal is and the way you try to make the template that describes it. So what they do, what you might expect them to do, what we expected them to do, was take two signals from two detectors and compare the signals. And when the signals look alike, then you claim you've seen an event. It's not what they do. they make separate templates for the two detectors, which are based on a very specific model. And the specific model, as I say, is the merger of two black holes. Then they calculate the correlation between their template and each of the data from the two detectors and make an indirect comparison. It's a little odd, but there's a reason for it. Not a good reason, but a reason. They make a big thing about this being numerical general relativity, by which one is to understand this is very difficult. But in fact, most of the calculation is really quite elementary. And over essentially this entire blue region, you have a post-Newtonian calculation here where, in fact, you get something that does exactly what I said. There's something with an increasing frequency. There's something with an increasing amplitude. And in fact, this frequency is determined by some mass and, of course, the relevant constants here. And this mass can be expressed in terms of the two black holes that are merging. This part is completely analytic. It doesn't take any effort at all to calculate. The ring down phase here can be calculated perturbatively, also relatively cleanly and analytically. And numerical relativity is in fact used for this tiny green region in the middle to tie the two onto one another.
Is there a way to get these powers, 1/4 and 5/8?
This comes immediately from a straightforward general relativistic calculation. There's nothing fancy about that, and there's no freedom in that at all. To put things a little bit into context, and it'll be useful, the frequencies we're thinking about here are on the order of 30 hertz. It goes up in this region to about 60 hertz. Up here it's about 150 hertz, and here again 120, 150 hertz. This will play a role as we go along. Okay. Now the data itself, we're going to see, is, as you could imagine, extremely noisy. The great problem with making an enormously sensitive detector is it also tends to be enormously noisy. And so many things have to be done. I'll show you the noise in just a moment, but it has to do filtering of very low energy information and filtering out of very high energy information to concentrate into things where they think there's actually a signal. And here is the way the actual numerical relativistic calculation would look. And you see this rather slow increase both in frequency and amplitude. And this is the actual template they use to compare with the data. And that's because they've done all kinds of things here. They've attempted to correct the empirical template for what they believe they know about the sensitivity of the detector and the kinds of filtering they actually do. Since the two detectors, in spite of their best efforts, are somewhat different, the two templates are somewhat different, which can complicate slightly the comparison of the two sets of results. And this is the calculation that they've performed, or the analysis they performed. This is the signal they get, and the claim is that it corresponds with a 6 sigma confidence level, which is extremely high, to the merger of black holes of mass 29 and 36 solar masses with 3 solar masses emitted in the form of gravitational energy. And the question, I think, that it's reasonable is, so what could be wrong? Is there anything that could be wrong? Yes?
Are you going to show us the second data from Hanford?
The second event? Yes.
Second data, just you showed one detector and second detector.
Am I going to show you that? Yes, I will in a bit, yeah. So what could be wrong? And here I would like to suggest that what could be wrong is that the use of templates is a serious, potentially serious problem. Okay? And in order to suggest this, let me tell you where you can really use templates safely in data analysis. There's one case I know that's better than all others, and it's here. It's in catching speeders in the United Kingdom. Now, you might not think this has much to do with gravitational waves, but it does. The point is, as you can see from this image, obviously this is a speeder, and obviously because he's moving quickly, the camera didn't necessarily get his license plate in focus. So the question is, how do you take this fellow to court and get a conviction? And the answer is, you use templates. Here is the same license plate. I've managed to get a very much cleaner, larger picture of it. And fortunately, the British traffic police know that there's a prefix. There are then up to 3 numbers. There are then 3 letters, excluding I, Q, and Z. They know there's an 11 millimeter gap between letters and numbers. They know there's a 33 millimeter space here, and they know the type fonts that have been used. The number of possible templates from a UK license plate is finite. They know them all. So when they do a little image enhancement by comparing this very unsuccessful photograph with the templates themselves, they come up with 100% certainty as to exactly what the license plate was, providing, of course, it wasn't a continental license plate, because then everything goes wrong. So the difficulty with using templates is you have to allow for the fact that you have a complete, or you have to make the assumption that you have complete knowledge of all possible sources for the event that you're looking at. And if you don't have that confidence, if you don't know that it's the merger of 2 black holes with 100% certainty, which means you have to exclude all terrestrial effects, all other possible cosmic effects, you have to come with absolute certainty. Otherwise, you have to correct for that. That will reduce significantly the confidence level you have in the results. And that's where things can go wrong using templates. So what we wanted to do, and this was the initial concern that we had, was what are we going to do to avoid this problem with the templates themselves? And that was simply to do a template-free analysis. We tried to perform things that were as close as possible to the strategies that LIGO had adopted, doing everything except, in fact, using the templates themselves. So the idea first is to construct the power spectrum. We have a record from the 2 detectors in LIGO, which is 4,096 seconds long. Given the fact that the actual gravitational wave event lasts for about 200 milliseconds, that's plenty of daylight on either side to get a good sense of what's going on in the nature of the noise in the data itself. Then following LIGO, we'll filter out very low and very high frequencies in order to get rid of the dominant sources of smooth stochastic noise in the background. We will then discover, as LIGO discovers, that there are simply an enormous number of very strong and very powerful narrow resonances in the system. Now, these narrow resonances cannot be the source of gravitational waves. So it has to be, those can be removed. And from this, we will construct a clean time record, which we can then Fourier transform back into the time delay. Look in this interval of plus or minus 10 milliseconds in order to look at the correlation between the 2 detectors and see if, in fact, there are satisfactory candidates for gravitational wave events. Now, one of the things that I want to emphasize here is that the resulting frequency range, which will extend between about 35 and 350 hertz, is really quite narrow. And this is going to set significant restrictions on the kinds of black hole masses that can be obtained. And in fact, recent calculations that were published in fact, the end of last year, suggest that masses much larger than 5 solar masses are disfavored as having a potentially observable effect on the nature of the cosmic microwave background radiation itself, changing the shape of the spectrum. This is a little bit like the greenhouse effect that we find on Earth, where the greenhouse effect itself can alter the Earth's spectrum. So there's some concern that we may be looking in a dangerous region here. But let's go see what happens. There are a lot of things that get somewhat confused in all of this. Words that appear to mean something, and it's not entirely clear to me what they always mean. What is non-stationary noise? Indeed, what's stationary noise? In fact, what's noise at all? We can start with something that's pretty simple, which is the question of stationary noise. And generally speaking, what that means is stochastic noise that's drawn at random on a distribution whose parameters don't change with time. Non-stationary noise, which one absolutely assumes is at the heart of the LIGO data, it involves this stochastic process, but on the distributions whose parameters do change with time. And noise in general is, of course, anything except the signal that you really want to see. And that can be really tough to nail down. These are not silly questions. The ideas get confused rather badly. This tells you something about the noise. And here, look at the scale, because the scale is really pretty incredible here. This is the strain that's expected. The total noise is in black. And there are a variety of things that happen. And this, perhaps, is a rather messy figure. But just wait, it gets worse. In particular, if we look down here on this rather low frequency noise, we see in particular one of the dominant problems here is seismic noise. At low energy, seismic noise is really terribly serious. There are also problems, thermal noise here, quantum noise, etc. Many, many varieties. And what you see, in fact, is that there's a kind of minimum here in a range which goes, roughly speaking, from 30 to a couple of hundred hertz. And that's the region in which LIGO actually wants to work. So in fact, what happens is that the LIGO team has chosen to simply filter out everything below 35 hertz. It just is thrown away. And you can see this is a logarithmic scale in the power spectrum in the strain. And here to throw out everything that's greater than 350 hertz. So there's a tremendous filtering of the data that goes on. And we'll do the same thing. Okay. Here's the real problem. It's the narrow noise. These incredibly narrow peaks. And I'll tell you that these peaks are seriously narrow. Here you can see some of them. Remember, this is done in the United States where power runs at 60 cycles, not at 50 cycles a second. And so it should hardly come as a surprise to you that here at 20, 30, 40, 50, 60 cycles, there's a very large and very narrow peak. The width of this peak is on the order of 20 millihertz, very narrow peak. And not surprisingly, if there are peaks at 60, there'll be peaks at 120 and 180 and 240 and 300 hertz. There are other peaks here which are even more serious. There's an absolutely enormous pair of peaks here, which in fact are so big. Well, look at how big they are. This is the region they're interested, 10 to the minus 22 strain, 1, 2, 3 orders of magnitude and more. And these are calibration lines that they introduce into the system itself. Calibration lines that have a very large intensity and in fact, I think we'll see have some serious consequences. But in any event, none of these things have to do with a gravitational event, which is expected to be visible on the order of 200 milliseconds. And a simple kind of uncertainty principle argument tells you that these are not going to contribute.
Why in Livingstone, these 60 hertz is much higher noise?
It is not only much higher noise here, these are not constant. If I look at the overall noise level here, the noise level can change by factors of order of magnitude 20 or 30 over periods on the order of half an hour. So at the particular time when this was taken, Livingston was larger than Hanford, but there are times when it's the other way around.
So it's actually
it can go the other way around.
So it's not stationary.
It is not stationary in any. Well, I mean,
but it's changing in this variation. From 10 minus 22 to 10 minus 24.
That's yes. So it's serious.
Why do the calibration peaks don't have harmonics, or very small?
They do have harmonics.
But much smaller than the.
Some of them are, some of them aren't. There are order of magnitude 20 calibration peaks sitting around in here. I mean, the narrow resonance structure is very serious here. And again, it can have, as we will see, somewhat unfortunate consequences. Remember, too, that essentially everything of higher frequencies here is just thrown away. Everything of frequencies here and below is thrown away. What's going on here is a little troublesome. And this will be troublesome in the subsequent data analysis. The problem with all of this is once you've cut down to this very narrow region, as I said before, you run the risk of throwing away all kinds of effects. And it's like this cartoon, which you've probably seen. This cartoon, I think, is probably close to 100 years old now. The fellow says to the policeman, "I'm looking for my quarter. I dropped it. Did you drop it here?" "No, I dropped it down the street." "Why are you looking here?" "Because the light is better here." And in a sense, that's what LIGO is doing. They're looking there not because they really want to see 30 solar mass black holes. They're looking here because, in fact, it's where it's easy to look. It's where the detectors are as noise-free as possible. But what happens if we do this? Filter away the low frequency information, filter away the high, clip all of these narrow resonances, and then make a Fourier transform back to the time record. And, well, you can't see it here. Actually, this is before I did the clipping. And that's because, of course, the noise is 1,000 times larger than the signal. But when I do clip, and here's the clipping itself. Whoops. Let's go back. This thing is not behaving. Yeah, this is the power spectrum that one gets from a smooth cutoff here in the frequencies, and then clipping the narrow resonances. And one can see this is the power spectrum that you would get over a very long interval, 4,000 seconds, and this uncertainty reflects the non-stationarity of this noise, which can vary enormously. Okay? This is what we've done. And now it becomes a little easier to see the signal, but not a lot. Here, just to do this in pieces, I first do the filter, the bandpass filtering, but don't do the clipping. And here you can see in blue what the actual signal looks like, but multiplied by a factor of 100. So this is after considerable cleaning has been done, and you still see a factor of 100 difference.
So
in the
red
signal.
is the noise, or by red you show here?
This is the result of the bandpass filtering. First,
Okay,
this is the raw data.
Why in this interval between 16 and 16.8, yeah?
This is
the level is much lower for the red, so the amplitude.
there are three different things shown here. The first is the black curve, which is the absolute raw data. That's their time sequence.
Yes.
The red curve involves the bandpass.
Yes, but
That has reduced the amplitude by a factor of roughly a factor of 100.
why actually is reduced between 16.4 and 16.8? Why the amplitude is twice less than between 16, 0 and 16.4?
That's a beat effect. That's a beat effect, and I will show you where that comes from. That's due to beat effects between calibration lines in the data, as far as we can tell.
So black one is the raw data.
Raw data.
Where, in which detector it's?
This is Hanford because that's the cleaner detector.
Okay.
And the red is bandpass filtered but not clipped, and then blue is bandpass filtered and clipped. And you can see the data here again. It's pretty much visible there. And if you actually look at this time record a little, take a step backward and see how it looks, you can see here the beat frequencies that are rather characteristic of these lines, and that is in fact the LIGO event. It sticks out. You don't need to do template analysis to find that event. This happens again to be Hanford. You will see something very similar in the Livingstone data. Okay? And no template is necessary. That's the crucial part of it. Okay? In order to compare two signals, we do what is standard in these things. We look at something called the Pearson cross correlation coefficient. It's pretty simple. That you take one record, time record here, normalize it, and shift it so that the average is 0, and then essentially look at the inner product of these two, allowing yourself to shift one of the records by some amount that's between plus and minus 10 milliseconds. and see what you get. And what you get is this. When the time shift between the detectors is 6.9 milliseconds, you see a very strong cross-correlation between the data. Here, just to gauge it, at 4 milliseconds, there's no correlation at all. This is, in fact, the time delay that LIGO claims between the two events. And again, this was done without any sign of templates, with a direct comparison of data from the two detectors. If you look at it a little more broadly, you begin to see this as a function now of the time delay, a very clear and pronounced minimum with a very high degree of correlation between the two detectors in excess of 0.8. Whether it's plus or minus is irrelevant. It's the magnitude that counts. And this, in a sense, was our confirmation of the existence of an event, but not of the nature of the event. So there's something there, but we don't know at this point what it is. And there is a time delay, which is, roughly speaking, 7 milliseconds, which is in complete agreement. Now, as far as the Hanford and Livingston data, here they both are, one can see here that the first 100 milliseconds of this event doesn't show any real characteristic structure at all. And then there's some rather pronounced peaks here, appear to be in both data sets, both our analysis and LIGO's analysis, is increasing frequency, largely speaking increasing amplitude, and then something which you might convince yourself is a ring down. And the same thing is true of the Livingston data. And what I would emphasize here is that the cross-correlator between what LIGO says is the Hanford event and what we get is an absolutely extraordinary 0.97. The same thing is true with the Livingston detector. And here you can see the black curve is LIGO's result. The red curve is ours. Theirs was obtained with templates, ours without templates. You don't need the templates.
And if you would cut, for instance, this diagram by 2,
yeah,
and then make cross correlation of this left side,
yes,
you get practically zero correlation.
you get very little correlation. That's right.
Very low, so
yeah,
there is nothing. So all correlation comes
that's right.
How many peaks? 1, 2, 3, 4 or more?
Yeah,
or you check it separately.
roughly 5. It's roughly roughly this 80 millisecond region here. That's reliable. That dominates. The interesting thing is that if I look at the correlation between this result and this result, which is the one that matters, that's nowhere near as impressive. It's still good, but it's nowhere near as impressive. But what it certainly indicates to me is the templates here were completely unnecessary, since the agreement of a template and template-free analysis is so much better than the agreement between the two detectors. You don't need this. And this is, in terms of the data itself, something on the order of 6 to 7 sigma. And you can check this out by taking a look at the correlations in the individual detectors with the so-called signal that I just showed you, and looking at 200 millisecond intervals and simply following what happens to these cross-correlators. There's one and only one unique peak here, which is indeed at the order of 6 to 7 sigma. And the question is, now that we've seen it, what is it? So we agree with LIGO that there's an event, but at this point we have no view as to what that event is. Okay? So and that's essentially what I've just said. The problem with all of this is that there's a second LIGO event. And the second LIGO event basically is invisible, as I will show you in just, just a moment, and can only be seen using template analysis. So the argument goes, use templates or demonstrate the validity of templates in detecting the first event, use the templates as a crucial step in seeing the second event. And that's a fine argument, except for the fact that you don't need templates. You haven't provided any argument in favor of their use. And here's the second event. Look at this event. It's absolutely beautiful. Here's the template. Here's the actual signal. I think you really have to be part of the LIGO team to see an event there. If I look at the noise in the two cases, here the red is the noise spectrum during the second event, In the significant region in here, it's substantially larger. The signal is substantially smaller. There's roughly a factor of 10 change in signal to noise ratio. And again, in both of these cases, it's much noisier in the second event than in the first event. We see absolutely no sign of the second event, nothing.
In fact, here the ratio of noise to the signal is more than 5, I guess.
Yes.
In the first event, the ratio of signal to noise
Was 2.
2. No,
So it's a factor of 10.
3 maximum.
Yeah, all right.
But it's okay. 3 already
Yeah.
for this is okay. But
There's nothing here. Okay. And now let me tell you something. What am I doing here? Now, I don't know why it did that. Oh, there's one possibility it could have been, which is kind of fun. During, in fact, the first gravitational wave here, there was an absolutely violent thunderstorm in Oklahoma. And it turns out that if there had been lightning there, by the way, all of this stuff is on the net. You can find thunderstorms for any 10-minute period you like on the net. They're all out there.
it's for the first event.
This is for the first event.
But these thunderstorms they didn't report. They reported for the second event.
Yeah, but
Thunderstorm.
there's a thunderstorm right there.
Right in between.
And this is within the 10-minute period of the LIGO event. Now, I'm not saying it could be like that. But I want to look a little bit at morphology, and I think it's relevant here. I'm sorry, I can't hear you.
The thunderstorm now was for the event where you don't find
No, that was for the one where we do find something.
okay.
Yeah. So here, this is really deep. And if you've all seen this, I don't know, have you seen this? You know who these guys are. This fellow over here, you know him. And that's the Planck satellite. It's easy to confuse them. And what we know is that in each case, we can decompose either of these images in terms of an amplitude and a phase. Okay? No problem. But what happens now if I do something that's very rude? I'm going to take the amplitude from the Max Planck satellite and the phases from the Max Planck image and mix them. Now, there are several possibilities. I could get the Planck satellite, I could get absolute garbage, or I could get Max Planck. Do you know which one we're going to get? There it is. This image was obtained by using the amplitude from the Planck satellite and the phases from Max Planck. What do we learn from this, aside from that? This is kind of cute. And although it didn't involve Bessel functions, I think Sommerfeld would have approved of it. I think what we learned is that the morphology of images, of which we're looking at a very simple one here, is in large measure determined by phases and not amplitudes. And the power spectrum, which is explicitly a problem associated with amplitudes, does not tell us the entire story. Okay? I think this is such a wonderful image. There it is, and then you put them together. Okay? Okay. Now, Virgo, who of course was part of this experiment, had a very useful PDF file, and still does on its website, which unfortunately was the wrong PDF file. You can check this out on the Virgo website. And it's the wrong PDF file because, in fact, there were some authors' comments in blue that were still in the version. And so after Dr. Robinet looks in some detail at the signal amplitude in this section called signal amplitude and phase, he makes the comment to remind himself, say something about the phase. And you know what? He never does. And I think it's a little worrisome. So let's say something about the phases. Because what we would expect from all of this is something very simple. Yes, there'll be some amplitudes and there'll be some phases. And by and large, the phases ought to be random. If I look at the Fourier transform, because overwhelmingly at the level of 1,000 to 1, what we have is noise and not data. But look at the phase correlation. it's pi by 2, minus pi by 2, essentially across the entire frequency they look. These are not randomly distributed phases. Even in the Livingston experiment, which is a substantially less sensitive detector than the Hanford, there's a strong evolution of the phases and nothing that could ever be confused with a uniform random distribution of phases, which would be the case if we were looking at proper stochastic noise, stationary or non-stationary. So there are correlations here in the phases which have not been taken into account. In fact, they have not even been discussed.
So you mean now you subtracted signal and then you look for the...
This happens to be the raw data, but if I had subtracted the signal, I would have gotten identical results. The signal is a tiny contribution.
It's
tiny. So there's a strong phase correlation.
It's super strong correlation.
It's super strong correlation. Now this can happen in a number of ways. This is the only slide with equations, and it can happen from edge effects in Fourier transforms. Whenever you do a Fourier transform over some finite interval, you use functions that are orthogonal on that interval and are essentially, for that reason, periodic on the interval. If you happen to have a signal which isn't periodic on that interval, which is to say the two endpoints are not the same, you get these endpoint effects which show up here as, look at this, k over k squared, non-uniform convergence. And that is a non-uniform convergence explicitly in the imaginary part. And if the imaginary part dominates, you get signs of plus or minus pi by 2. So this can be things that are related to non-uniform convergence for technical reasons, but you have to find out about this. You have to consider it. And as you can see, I mean, with non-uniform convergence, it ends up at something which is conditionally convergent in the middle of an interval and really diseased at the ends. And if you actually look at what happens when you Fourier transform the power spectrum back, you can see exactly these effects.
They didn't make these.
They didn't. But they didn't report it. I don't. I can't. I don't know if
they didn't report it. Then it means that they didn't make it.
Yeah. Perhaps. That's, I think, the most positive thing one can say.
No, but then it's not even noise.
No. But this is a possibility that, of course, they have to rule out. They have to demonstrate what's going on with the phase information, and they haven't done that. Okay. Yeah. If we go on and imagine we start to shift the signal, what I show you here is what happens if I bandpass bandpass filter the signal, but I don't clip any of those narrow resonances. And then I start to change the time delay between the two. And now again, we have a completely dominant, noise-dominated signal here, but lo and behold, there's a 7 millisecond time shift between these noise-dominated signals. Said another way, if I take the signal, if I remove the signal from this data, then I discover an extremely strong 7 millisecond correlation between what should be pure noise and the signal itself. And this is not acceptable again. See, this could be an unfortunate accident. And here I could show you, this is what happens before the shift, and look at what happens when I shift the data by 7 milliseconds. They just line up with one another. Okay? And here in particular, the place where we're most likely to think the problems lie are in calibration lines, which are slightly different frequencies. And these are things which I say can show beat frequencies. They show beat frequencies internally here and here, and then the two sets show a beat frequency against one another. And when I shift the data only including these calibration lines by 7 milliseconds, they're brought into phase. And again, this is an effect that's 1,000 times larger than a signal. Removing the signal is absolutely irrelevant here. So I think that there are reasons why one should be just a little bit concerned about the nature of this analysis.
But if you take other time interval when there was no this event and make similar analysis, what you will get for the noise cross correlation?
one can see similar things. One can see similar things in the noise cross correlation.
So you mean that all previous records, when there is no claims that they see the signal, you again have correlation?
There are correlations that persist. They're not as good as this one, but there's still correlations that persist. Yeah.
No, but they are not at the same significance level.
No. So I mean, I can't explain everything that's going on, but
No, here extracting you have signal helps a little bit of producing anti-cross correlation or correlation whatsoever, yeah? Because it increases actually significance of correlation.
That's right.
So you could take what you was calling noise and then add on the top of what you had and then call it signal and make the same output.
You could do that. You could do that.
Even if they are completely
Yes,
different.
you could do that.
And
Yes.
they should be perfectly the same, by the way.
Yeah. So there are problems here, and I would as I say, what I'm worried about. Several things. There are some observations I'd make in general terms. First of all, the use of templates in an analysis of this kind can be misleading in regard to the estimating the confidence level of any kind of detection for any signal. You simply have to know for sure what is the probability that any signal that you might get is in fact covered by your templates. And if you multiply that even by as large a number as 90%, you suddenly discover that what was a Six Sigma event degenerates to next to nothing. I would also argue that phase information cannot be ignored. You'd like to tell the difference between Max Planck and the Planck satellite. You should keep that in mind when you do analysis.
But if there is actually so strong phase information, it means that it's not random noise.
Of course it's not random noise.
What knows what,
It is.
you see?
The point is we should know what. It's,
No, they
I mean,
should know
yeah,
what
well,
to
no, all right.
So,
I mean, I just wasn't going to leave it up
but
to
you
God.
cannot just ignore this.
No, you can't. No, you mustn't.
Pattern and call that it's noise without knowing the reason for that.
Right. The other general comment I would make, which I think is important, is to go back to LIGO's own history. In the beginning, LIGO said very, very clear, beginning meaning before advanced LIGO was online. They made a much more sensible statement. And the sensible statement is that LIGO can provide certain information, but in fact that real confirmation, both of the discovery of a gravitational wave event and of its interpretation, should be based on many different experiments, of which LIGO was one. And I think there's quite a distance between that more modest and more realistic view of things and the somewhat greedier notion that they had discovered everything at one time. And as far as I'm concerned, I have problems. My problem is that I have a great difficulty trusting in all details the analysis been presented by LIGO. The fact that both the gravitational wave and non-gravitational wave components of this initial event show the same 7 millisecond time delay between Hanford and Livingston has the unfortunate consequence that honest people can actually disagree about the interpretation of the event. Now, as far as I'm concerned, LIGO is making a claim of an enormously important discovery, and it must not be wrong. I mean, I spent much too much time working in an area of heavy ion collision physics, where the holy grail in this case was not gravitational waves, but finding the quark-gluon plasma. And the number of times when the quark-gluon plasma was rediscovered is almost without limit. And the fact of the matter is that there's no compelling evidence that it's ever been discovered. The consequence of this has been that the field has largely been rendered irrelevant. And I don't want that to happen here. I think we all have an obligation to get involved with this, and if we care about what's actually going on here, we have to try to get things sorted out.
Then also, Andrew,
Yeah.
I don't know. You said, typical frequency of these 4 peaks is about 60 Hz.
Yes.
And it's precisely at the point where you have this body resonance, okay, due to the electricity.
Of course.
Yeah? So
Look, it is absolutely extraordinary. They did not build a satisfactory Faraday cage. I mean, for goodness sakes, they've spent $1 billion on this experiment. One could ensure at least minimal isolation of the 4 kilometers of fence. It's much less expensive even by the meter than Trump's fence. and it doesn't take much more than chicken wire to give you perfectly adequate. These are very low frequency things. You don't need a high density mesh. You just have, talking about 300 hertz or 60 cycle multiples. It doesn't take much to screen this. Right? There are many things that could be done. And indeed, if you look at some of the technical publications from LIGO, they make it clear that precisely this kind of electromagnetic insulation of the device has not really been given adequate attention.
Statistic of this fluctuation of the level for 60 hertz line.
Yes, that's on the net. Everybody can go into the computer and look up stability of the 60 cycle lines, and you can see an instantaneous indication of it. It matters, by the way, that this is stable. It matters so that to the extent that if the frequency shifts by more than 20 millihertz, there's actively make an attempt to correct it. When it exceeds 50 millihertz, they really take this very seriously indeed. So there's an attempt to stabilize these things. In the same way, there's a strong attempt to minimize harmonics that are actually transmitted along the net. All electric transmission, almost all, is done in 3-phase transmission separated by 120 degrees. And even harmonics there can be very, very serious and detrimental to electric motors, so that there's every opportunity and exploited to remove at least the even harmonics in the 60 cycle. So, but all of this stuff, there's data there. One can learn about this in great detail, and you can see it in the LIGO data. There are some peaks, for example, which are clearly Gaussian. The 60 cycle is clearly Gaussian. It shows the fluctuation in the frequency. But there are other narrow resonances in particular that are standard Lorentzian types, which are natural resonances in the system itself. And when you see this change of sign on the curvature in one case and not the other, I mean, you see things that are absolutely clearly telling you the nature of the noise sources themselves. There's a great deal one can say here, and it hasn't yet been said. The one thing that, I mean, I apologize for being so negative, but the one thing that I think is really tremendously important is that LIGO has put relevant data on the net. It's there, and you can download it. It's simple data sets, the data analysis not hard, and it makes it possible as if for all of us to understand what LIGO did rather than simply believe it. And the more data that's out there, the better. The surprising thing, as I said at the onset, is that very few people have chosen to make use of any of this data. And it would appear to me, in some respects, that the desire to believe has triumphed over the desire to understand. And we're a little bit in the kind of Donald Trump world of alternative facts in physics, which I don't feel at all comfortable with. I would also say that data is resulting from 40 years of work, and $1 billion investment merits serious analysis. Do not believe me. Don't believe LIGO. If you care about whether or not gravitational waves have been observed, download the data and look for yourself. It's the old-fashioned way to do physics, and I think it's the only one you can believe in. In any event, more data is coming. More stations are coming online. If we wait, and I hope to live to see Lisa come online, they say 2034, but maybe before. We're going to find out, and perhaps it would be a good idea to wait with the champagne until we have a little bit more compelling evidence. Okay? And that's what I'd like to tell you. Yeah.
I'm asking for this correlation which you found. This was two-point correlation. Would the data allow to go to higher point correlations?
I mean, if there was another detector. Absolutely. Absolutely. And it would introduce an extraordinarily impressive level of agreement if you got 3 detectors. I mean, we'd be up to something on the order of an accidental possibility on the order of 10 to the 12.
But you can calculate also correlation for high moment.
We could, sure, but
because it will point out you comments.
we could there are 2 ways one can go. One can look at more detailed comparisons of the morphology of the signal, and that's one option. And the other is, I mean, if Virgo had been online and fully functioning at that point and simultaneously made an observation.
Virgo is going now to be involved, but at much lower level of sensitivity.
I know. In point of fact, if I actually look, because one question one can ask is, since the Livingston and Hanford detectors are really quite different detectors, even though they were designed to be the same, they're in practice, Hanford is a better detector. So one can ask, what is the relative role? In fact, in determining the actual shape, Hanford is dominant, completely dominant. The primary role of Livingston is merely to confirm the existence of a similar event, not to determine the shape of the event. And so if something is sensitive enough to provide a statistically meaningful correlation, it doesn't have to make a big contribution. But that's also the dangerous part of it.
But also could be actually some kind of unhappy fluctuations for this.
Well, that's...
Is the right, because you also have perhaps separately on 2 detectors. If you will, are there similar events which are not correlated but by factor 2, for instance, above the level of noise?
Right.
Of course.
That's,
And how many of them? Oh, you can calculate. If it would be random noise,
yeah,
I'm
yeah.
sure you
If it's random noise.
yeah.
But of course, there are these other possibilities, because they say there are things that are not stochastic in any sense of the word. There are these calibration lines which do have absolutely trivial interference effects, beat frequency phenomena, which are there to be dealt with. Yeah.
Is the location of this thunderstorm in Oklahoma consistent with 7 millisecond delay?
I think it was 5 milliseconds.
Okay, but it's 7 milliseconds.
But it's, yeah, but thunderstorms are big.
You do not know how it propagates in the atmosphere.
No, that was, I think, meant more to be rude than to be instructive. These thunderstorms, this is actually not an insignificant distance. This was actually a little, right around 5, but you can see there's also something violent going on up in Nebraska, and these don't show. There was something like this, tell me, during this 10-minute interval, there were 399 lightning strikes in here. I mean,
I can see the points that you made that a wrong template will give you both false positives and false negatives. But if we now come to the specific event, in quotes, event which seems to be there, I wonder how much are thunderstorms significant here? I mean, thunderstorms are not exactly an unusual occurrence in the United States.
No.
Obviously, some of the worst ones in the whole decade.
No.
You should be able to see like events like you're seeing there probably every couple of months. So have you looked at a broad patch of noise to see if there's...
no, I haven't.
And then the
But-
second question...
But that's not an irrelevant thing to do, and it's a perfectly possible thing to do.
And then the second thing I wonder is, and not just speculating, I mean, when you have a big power grid, usually the power companies synchronize their generators so you don't get any phase differences between different parts of the grid. So now 60 hertz, what is this, 60 milliseconds, 70 milliseconds. So now you shift those 1.78, 7 milliseconds. So that would be 120 phase or some 180 phase. So I wonder if this was maybe the phase between different parts of the United States power grid at that state. Maybe especially because when there's that change, and especially since the 60 hertz, this component might be sort of dominating like the correlated noise.
Yes.
So is it possible to get any information from the power companies? Do they have any data on that?
They have data. Some of it is proprietary. You have to pay for it. and some of it is free, and that's what I looked at. And so you can get certain statistical information, but there's more data available. It's terribly important to the power companies to keep regulating this. And they do all kinds of things that one doesn't know they do. For example, if you have these even rather small millihertz changes, your electric clocks soon show the wrong time. And so they keep track of the integrated phase as well. And several times each day, add or subtract, make intentional adjustments to bring the integrated value correct.
I just read at that point if they made some adjustment, they would.
Yeah, I don't know. Yeah.
So what is so you showed this time shift
Yeah.
in calibration resonances, and surely that you can observe or measure all the time. Is this changing since 7 milliseconds, or is this how stable is that?
It changes.
So that should be there now.
No. It would be there if there was an elementary rational relationship between the phases of these things. Let's see if I can bring up the actual. Yeah, these are the actual frequencies for Hanford: 35.9, 36.7, 34.7, 35.3. So it's not quite so simple because they're going to change. It's not going to be a constant 7 millisecond shift. You've got 4 frequencies that are beating against one another, and it's true that after a certain amount of time.
Maybe I misunderstood what these calibration lines are, but that's something.
They're mechanical oscillations in the system. Yes, but they go in and out of frequency, in and out of phase with one another because the rational relationships are not trivial. Oh, of course it's deterministic.
I completely understand that.
Yeah.
Once I understand it once, I understand it forever.
Oh, you absolutely. Oh, I mean, absolutely, and you can follow. You can follow this without any difficulty, which is, of course, what we did. We looked at this 4,096 second record over the entire record. It just made exactly this filtering to see what they were doing. And sure, you can see it.
Just one more question concerning the thunderstorm. I mean, this is just placed in the line, okay? But would you see the same effect if the effect is due to the thunderstorm if you put placed somewhere?
Oh, sure.
Okay.
Sure.
And this could be screened by which they didn't do it, as I understand. The effect, I mean, this is an electronic.
Yes, and of course it has the 2 possible ways it could be transmitted. It could be transmitted directly. It could be transmitted through the net itself, and then one has to decide. But I mean, I know there's some people like Slava who are absolutely crazy about having high quality sound on their and if you really want to have high quality sound on your home stereo, you shouldn't deal with this dreadful frequency variations and phase variation. You should have pure, well-filtered electrical sine waves.
I already realized that I have to be screened from 60 Hz gravitational waves.
Yes. And the point is that you can go to your neighborhood audio store and buy a clean source of 50 cycle power here, which is free of all of these things. And I don't see any reason when you invest $1 billion in this, that they haven't made absolutely certain that their power supplies are completely stable, both with regard to frequency and amplitude.
You see, I think sure there will be some kind of strange thing, because right now I do not know what was the source of this. But imagine that it will remain the only event, because now 3 months running, nothing about the level of noise. Otherwise, I suspect that they would say, they have some 6 suspects. But nothing like this one is coming. And if it would remain like this one, then what you can trust? You cannot make judgment on the basis of one event that you are able to use templates. They have to have at least 5 or 10 of these. Even if it was gravitational wave. Because, okay, you can say For instance, in past there was one reincarnation fact, yeah? But it doesn't make the thing statistically significant that we know that, okay, this field about reincarnation is called religion, but not physics, right? So here is the same story, actually, as I said, irrespectively what community thinks, because all American things that they are first, of course, yeah? Right. But irrespective of these things, the only criteria in science, as I said many times, okay, it's not advanced study institute, it's not principle, it's experiment, yeah? And you can make only your own judgment if you care really, but not based on the rumors or on the general conviction of the whole society or matter.
I mean, now that you've raised the level, I would say, yes. I think we're entering a new era, both in this kind of astrophysical phenomenon, but also in astroparticle physics.
Yeah, right.
Because we're reaching a point where what we could expect to see is more and more experiments that are done on the basis of single events that we didn't cause to happen.
Right.
And under those circumstances, we have to be absolutely sure of the interpretation of the data and the way that was arrived at, because we're not going to be able to do what we used to do and go out and repeat the experiment and confirm it, because we won't get the same event. We didn't create the event. And so one way or another, if we're going to continue to do big and expensive science, we have to find ways of creating and establishing the kind of confidence in data that we're used to having from doing physics the old-fashioned way, of actually going out and checking the experiments are right.
But this is not strictly true in the case of LIGO, right? Because, yeah, sure, if this is the only 3 events that we see, and we see no more from LIGO, then of course we should be skeptical. But we expect much more events from LIGO, and like Hydra comes on LIGO, expect
But
more
we do
events.
not see by the way 3 events. You have to understand, the only event which we really see above the level of noise is the first event. Second event is rubbish, okay? Its statistical significance is much less than 3 sigma. Why? Because people use templates to extract the things from the under-level of noise, you see? Therefore, you have to believe that it was like this kind of thing. Therefore, you cannot use second and especially third events to confirm or disprove anything. The only thing actually which is reliable, if I'm right, yeah, is the first event, because you see these 4 peaks. The rest, you can, okay, this bell and preface, you can forget, because they are also under some kind of strange noise, okay, which is strongly correlated. What does it mean, this noise? Yeah.
But this criticism is fair only if we don't see any more events.
Absolutely.
So
Yeah. But
sure,
you have to see more events, not like second and third.
Yeah, of course, you have
to see like first event. But now there is 3 months running, okay, with 20% better sensitivity. And I asked, they are not going to give any next press conference in the nearby future, as I was told, okay? They want to shut it down for 1 month, then involve Virgo, which will have much less sensitivity, but you understand that there is other way also, what Andrew said, okay? To identify astrophysical source, and then look using templates. Then after you have this astrophysical source, you can use templates. Nothing wrong about it. And here, you don't know from where it came. I think it's 4,000 square degrees of region which they can now identify like most probable.
If LIGO comes with more events, we'll be delighted. We will, of course, take a look at them. And I would hope that we would confirm, once again, that what they've seen is true. And I would hope that we'll be in a position to say, yes, they did. I don't have any particular desire to destroy these people. What I care about is that if we claim we've discovered gravitational waves, we really have. I mean, consider the alternative. Imagine that we all believe we've discovered it and we haven't. Everything you build on that is garbage.
This is fair enough, but like all of this with lightning storms, and it could be this, it could be that.
It's
a bit annoying.
No, discovery of electricity.
I would say what is there's a question here, which is a question on whom does the burden of proof lie. There's a very interesting possibility. If you're going to be charged with a crime, a good place to do it is Scotland. And the reason is that they don't have two verdicts in a Scottish court, they have three. You can be guilty, or you can be innocent, or the judgment can be not proved. And not proved has the same consequence as being found innocent, except for social approbation, which is serious. And what I would say here is that it is the burden of proof on LIGO to show us beyond any reasonable doubt that they have discovered gravitational waves. And I'm not saying they're wrong. What I'm saying is I don't believe they've proved their case yet. If I were to tell what I wanted to see, I would like to see that their case is proved and that we do discover gravitational waves. And sooner or later, I feel personally confident that we will do so.
So I guess I understand your positioning, and you made, I guess, two remarks based upon your analysis. One is this curious coincidence between beats to 70 seconds. That's important thing to know. But another space progression I couldn't quite understand because you brought it up, but it didn't really follow up. So, for example, could you go back to the slide that shows the phase correlation?
Mm-hmm.
So what's the x-axis here? This is the, and what's
this is
showing
what we have here.
So the contour plot. Yeah, contour plot.
Right here, look.
Right.
Yeah. This is the first of all, we're looking at the Fourier transform of the time record. This is the amplitude.
Yes.
This is the phase.
Yes.
And then, of course, there are an extraordinary number of points on here, and so the question was to look at a contour plot of where the phases lie.
So x-axis is the frequency?
So this is the frequency which is covering essentially the entire region that LIGO covered, and then the contours are showing you the density of plots.
And you said this phase correlation could be explained by the fact that you compute Fourier transform with leads.
That is one possible explanation.
So if that's the case, then what does this actually? Why are you worried about this?
Then it's not. Then it's strictly a trivial analysis problem that you can dispense with. And the point is, one should demonstrate that that's in fact the case.
So if you take raw data, then from raw data you are getting this kind of thing, yeah?
Yes.
After you calculate this thing.
Yeah.
But then if you calculate this thing,
Sorry.
then you could actually take, for instance, more narrow range or much higher range.
Sure.
And what is going on? Just to see the boundary for calculating.
There are many ways. There are many ways you can deal with this. Yes.
But if you check it or not, actually, how it depends on this boundary, because you could check it with the same rotation.
We haven't done particularly extensive works, but it's a trivial.
What I see from you is that more serious concern is this chance correlation, chance coincidence that
that's right.
Correlation lines give you the same.
I mean, it could be since this 7 milliseconds is nothing. There's nothing sacred about it.
Right.
That if it was an unfortunate accident, then in another event wouldn't necessarily have this unfortunate accident. You would see quite different time delays for a signal and for the background, and then everything would be fine.
That's right.
Absolutely.
So I guess my question would be, what would have convinced you that this is a gravitational wave for this first event? For example, if you didn't see this calibration line causing the same time, then would you have been convinced? I'm just curious.
It's a question of what convinces me that it's true and what makes me worry that it isn't.
Right.
The thing that it would have been nice is if the LIGO process had followed their initial scenario, that they would come with a suggestion of where, when it was, and that other independent experiments would help to confirm.
Yes, the contour part would be
then it's dead.
I can agree.
But then anything short of that, then you're in this very unpleasant situation of having to rule out all other possible things, and I don't like that.
Actually, using LC5 wavelengths like this one, it's also quite convincing. But if it will be just one, okay, what you
That's-
can say
that
about
I-
one is
yeah.
fantastic.
Yeah.
You see?
I just wonder if I look at this noise plot again. Now, let's just invert the problem. What kind of noise source or perturbation would create perturbation which is strongly correlated in phase? But I mean, how would you wanted to generate this? But what is numerical manually, or by what sort of exponential perturbation should be generated?
So phase correlation occurs when you have non-translation invariant, non-station noise, to easily create phase correlation.
Yeah.
Yeah.
They can, yeah.
But this already depends on the window, right? If you just shift your window, this goes out. What you call zero phase depends on where t equals 0.
Sure.
So if you shift your window by your time window by a little bit, this correlation goes away, doesn't it?
It depends on the nature of the source. As I say, if you have a system like this, you can end up with problems.
Okay, good. So I think it's a good time to